Jonathan Moscatello. He's the owner of the heat pump store up in Portland. He is deeply knowledgeable, in my experience, of what's available in Asia because he actually goes over there and works with direct imports. And heat pumps, I've learned, they really never stopped being developed over in Japan, for instance, where they got ductless mini-splits in 1979. So Jonathan goes over and sees a fully evolved heat pump market that is kind of invisible to us in the United States. And so I was inviting him on to share that with us. Jonathan, welcome.
Hi, Sean. How are you today?
Oh, I'm having a great time. I'm just like dancing over here. I'm having such fun listening to these presentations. It's just, if anything, I'm just dying trying not to just jump in and talk with people. This is great.
I believe it. I believe it. So I caught a little of Amanda's presentation, and I'm pretty excited. So thanks for having me.
Do you mean Naomi? Naomi was the person.
Yeah.
Amanda is the
Thank
person
you.
facilitating the Zoom webinar stuff. Thank you, Amanda. This is working out great. And Naomi just presented.
So I'll just sort of launch into it. I am coming at this as a bit of a geek. I am enamored with heat pumps and got involved in ductless heat pumps pretty early. I'm not a mechanical engineer, though I work closely with them. My experience is more on residential and some light commercial applications of heat pumps. I live in Portland, Oregon, and worked mostly in Oregon and Washington. Through my work, though, water heating has come more, it's become more and more a factor, excuse me, in the work that I do. Amanda, please advance the slide. And in the recent years, my wife and I have found that we have a lot to share out in the marketplace. And so we started a consulting company, and she's running our heat pump, ductless heat pump residential contracting business. And in the last year, I've began working more closely with Northwest Energy Efficiency Alliance on the ductless heat pump, kind of out in the market, talking with other contractors and distributors and brands, and just trying to organize the market and educate the market. I work with Fujitsu General America, where I'm going to other regions of the country. And we are training contractors who really don't have any experience with ductless heat pumps yet. And then I have another company that I work for in Portland, which is a commercial building ventilation product, which is really fascinating. A passive house certified commercial building product, which is really kind of mind blowing how efficient it is and how intelligent it is. And then finally, possibly my funnest project is with UTL Air Conditioning and Electro Industries, and we're trying to bring to market really different heat pump water heaters. And so that's what I would like to talk with you guys about in general, is heat pump water heating, some of the potential and some of the challenges. So please advance the slide and I will launch right into it. Oh, that was my notes. Please advance one more. Okay, so why am I about to talk about the things that I'm going to talk about, which are sort of technical in nature? Why should we get excited about heat pumps? What are the things we should learn about? Well, if we go to the next slide, the real rub for me is that refrigerant is really a special product in terms of its ability to move energy over space, through a structure from one area to the other. And liquid refrigerant, if we're just comparing it to water, can convey 3.2 times more heat energy. Or if we're conveying vapor, it's 5.2 times. And if we are, we're building stuff, it's really becomes a really powerful tool for us to move thermal energy through a structure. And if we advance the slide, so these are some of the preconditions that I think of. And when we talk about refrigerants, we have to remember that there are literally hundreds of them licensed for use in the USA. And that they all have very different chemical properties, like their boiling point, their vapor pressure, latent heat, specific heat. And because of these different properties, they have different end use applications. So ultra low, so the terms that are bandied around are ultra low temp, which is related to industrial cooling, low temp for freezing food, so freezers at the supermarket and so forth. There's some medium temp products that are for space conditioning and water chilling, and then there's a typo there where they're medium high temp, which is what we are mostly working with right now, which are space conditioning and water heating. And then finally, there are a few high temp refrigerants that can be used in refrigeration only. But the real takeaway that we've got to remember so that we don't go off in some really unproductive areas is that the chemical is specific to the application because of its inherent properties. Okay, let's go to the next slide. Now, all refrigerants, when we're going to apply them in our world, pretty much need a compressor. And the compressor has two really important functions. It moves the refrigerant and it pressurizes or changes the pressure of them. But this is the really important takeaway that I feel like I need to set, set some understanding on, is that the compressor is specifically defined for both the type of refrigerant and the volume of refrigerant. So not all compressors are the same. The ones that work on ultra low temp look and use energy very differently than the ones for high temp. And then specifically, the compressor is sized or configured for the volume of BTUs that you would like to move for it. And if you go to the next slide, the next key point is that compressors use lots of energy, right? So if we're trying to work in an energy conservation design, we want to really avoid large compressors. And we want to avoid them running longer than they have to. So the directive for us, it should be to use more very small compressors that are specialized to their application. So the sort of, remember the low temp to mid to high or to high temp. Right, and in that way, we will get the energy user, the compressor, will be really optimized for its efficiency, and it will probably run less as a result. And then we always want to try to use DC inverter compressors, which I think most everyone, I'm going to assume most everyone on this call understands what they are. But the key advantage is they use much less energy.
I think that you should just briefly explain, or I'll say my understanding is that
yes, give the light.
Doesn't make them have to turn on and off, and that turning it on and off and on and off, as opposed to having its usage smoothed out by an inverter, makes a lot of efficiency gains.
Yes, Sean, you're absolutely right. And in fact, yesterday I met a Californian solar contractor at the expo, the Heating and Refrigeration and Air Conditioning Expo in Chicago. And he showed me some performance curves of his buildings where the short cycling or the compressor going on and off in homes just destroyed the beautiful design of these net zero homes, because the compressor would run really hard at a high volume and overshoot the production of the PV. And then by their nature, they shut off, and now we're underperforming on the PV. And if we had simply an inverter in place where the compressor could sort of match the need in the home, almost every home would have had operated below the PV production and left some additional energy for use. And that's because a DC inverter compressor uses less energy, but it also matches the demand and varies its output to match the demand. And it is powerful to see these images. Maybe some of you on the call have seen it. So for me, if we can use smaller compressors that are specialized to the application and use DC inverters, we will avoid large compressors, avoid long run times. And for us, large is actually not that large. 24,000 BTUs for residential application is about the middle range. Once you get over 24,000 BTUs, we find that they actually start to use a good amount of energy. So let's move to the next slide and I'll kind of round this out for us. All right, so what does this mean for us and what does it mean for water heating? Well, let's talk about it. It's pretty simple, but if we go to the next slide, one compressor rule them all. This is me trying to be funny. You know, that's Frodo from the Lord of the Rings and a little compressor. I am amazed at how many people in the utility conservation space, and even I think my friend Sean has fallen prey to this sometimes. They'd love to put just one compressor in a building and have that compressor make heat or cooling and try to do it all, hot water, and then maybe space conditioning. And if you understand that the compressors are specialized towards the I just got a funny chat. Thanks, David. That's pretty fun. If the compressor is sized for and it's chosen for the application and it's small and it doesn't have to run all the time, so many tiny hammers or many tiny compressors doing work appropriate to them, it's amazing what we can achieve when they are an inverter. So Amanda, please move to the next slide. So the other thing about trying to make one compressor do it all, which again, I find so many people are just really go down the wrong path to try to get there, is that manufacturers can really be successful when, in a general rule, they can be successful when they specialize, simplify their products, and then produce volume. And it's really kind of incredible some of the efficiencies you can see. And my message out of this is let a ductless heat pump heat and cool the space, an inverter ductless heat pump. Incredibly efficient and in its operation, highly specialized towards what you're doing, which is air to water vapor compression of a refrigerant. And they also are very inexpensive relative to the other options we have when you're just doing air. Then we can start to really get good as an industry and making heat pumps, and we can focus on heat pump water heating that just is designed around domestic hot water. And we're getting better and better at that. And it's this, if we stop challenging our manufacturers like we're doing on the West Coast with a lot of our utility programs to try to make one compressor rule them all, I think that we can really get down to brass tacks and get to what we really want to do, which is make better products for people in their homes that use much less energy and maybe have refrigerants that don't contribute to global warming. So let's move on to the next slide.
And Jonathan, to interject,
Yes.
because I want to reinforce your message here. I've had a lot of developers who don't want to change their floor plans, and they didn't ever put a space in for a tank because they're going to use a central boiler. I've had many different developers have the same thing of they want one compressor because they haven't made space for 2 or 3. And
yes,
and I think that it's hard to change developers. So there seems to be a place for central systems with compressors that are supposed to do all the same jobs, even though I hate them and I think they're less efficient and really frustrating to design and frequently don't work very well at all. Like all the things you're saying, one compressor is a monster. I hate them. I wish the whole design industry would just change. But it's driven in part by inertia. And
well, I mean, it's a good point, Sean, and I think we're also unfortunately at a period of time where we're really quickly don't have the heating and cooling equipment that we need to. And so in some of the really highly energy efficient, thermal efficient structures that I think you're working with, we often have these ductless heat pumps. They'll work just fine, but we also probably need them smaller, that produce less BTUs. And I know of a factory and a program, it's kind of hush-hush top secret, but it's too fun not to share, where imagine we have a simple wall penetration, like a wall heater for some of the accessory spaces, and it's a tiny little heat pump that makes a few thousand BTUs. So in some rooms or spaces, much the way we have, little zonal electric heating devices, we could have zonal heat pump heating and cooling devices that simply fit in a wall cavity. And I don't think we're far away from that.
Well,
actually.
isn't that like a PTHP, a package terminal heat pump that you're talking about?
It is, but it's like, what we know as a PTAC, or a package terminal air conditioner or air unit, is kind of like the horse and buggy. And I'm talking about something that's a little bit more like I'm trying to find it more like a Leaf in terms of its sophistication, right, and all those kinds of things. So I think we're. I mean, I guess you could probably still call it a PTAC, but it's just going to be much more compact. It's going to have inverter technology, and it's also going to make. And I think this is the key point, John. It's going to make a BTU output that's really appropriate for a very high efficiency structure, which may only need a few hundred BTUs per room.
Yeah, I mean, to that, we have buildings that in climates that have air conditioning and heating loads everywhere else, but the people in these apartment complexes only turn their heaters or coolers on one out of every 3 days year round. One out of every three. So we know there's tons of only tiny little heating and cooling demands that they would have.
So I just got a great question. So I guess there's some interest in this little Leaf PTAC, and I think it's in a very early development phase. It's in design. It's reaching some prototypes, but it's a total utility-driven research project. And I would say if anyone has contacts, we're looking for some investment at the utility level to move this product to market. That being said, we have brands in the US that would carry the product for it. But much like my water heaters that I'm going to show you in a little bit, these are prototypes that we need to connect through the marketplace at this point. So I'll keep moving here. Okay, let's talk a little bit about refrigerants, because I know that that's important. It's on people's mind. So we have two existing refrigerants that work pretty well for domestic hot water. R410A, which is our current typical air conditioning heat pump refrigerant, it's a medium temp refrigerant. So it's not super great for hot water, but it'll work. It's fine. But it has a high GWP, right? R134A is a so-called medium to high temp refrigerant. It's probably a little bit better, but again, it has a high global warming potential. The benefit, though, is that, of course, they're both widely accepted, commonly available, and technicians who would need to work on these out in the field have the requisite tools and experience. So, I think it's what we kind of have to work with in the near term. There's one thing I think that's really good about the heating and cooling industry is that once there is a widely accepted and promoted alternative, it can switch pretty quick. So I am comfortable personally saying, let's go to market with what we have. They are going to market these refrigerants right now. And when we have a widely accepted alternative, we'll switch pretty quickly. So let's move on and talk about some features. Let's look a little bit into the future and see what we're going to be working with. So what do we need from the next generation of refrigerants? We need a medium to high temp property, and of course a low global warming potential. And so I threw the R410A and the R134 on this. But the ones that we're looking at are R32. It's not licensed in the USA. It's being used in Japan, starting to see it in China, which is good. This is the product that, if any of you are familiar with this industry, it was developed by Daikin, which is a really well-known brand and a good, I think, a good industry participant. The ones that I also did some research on and found that I am actually kind of excited about is the 1234YF, totally early experimental product. But look at the global warming potential, 4 on that. It's a medium temp product, but like we saw with 410A, you can make a medium temp product work fine. The problem is, and I think it's a little bit of problem for all of these alternates, including R32, which I didn't write in that cell, is that they are somewhat flammable, with the, of course, exception of CO2. And so this gets some really, there's a little bit of concerns, and they might not actually be licensed for use in anything but a unitary product. And what I mean by unitary product, and this is a term that I think for people who, kind of aren't familiar working with HVAC people, a unitary product is something that is a single vessel or a single form factor. Like, think of your refrigerator in your house. That's a unitary product. Think of your a washing machine or a dryer. Those are unitary products. But your central air conditioner or something like that is a split system. And so it's, it doesn't operate on its own. It needs to be connected to something else. And so these alternate refrigerants like 1234, 290, or even CO2, they're going to probably be required either because of pressure or flammability to be a unitary product, which means we're going to have a really different kind of system that they're used in. Okay, let's move to the next slide. So what domestic hot water products are out there? Well, EcoCute, I came to realize in preparing for this, is kind of actually a terminology for something that uses CO2 as a refrigerant for hot water primarily. And I think if there are any utility people on the call that are working on the West Coast, there's a lot of people that are trying to use Sandin, which is available now in the US, as something that's both combination space heater and heating product, like using the hot water to maybe do radiant floors or a fan coil. And in Japan, they just really don't use them that way. They use the CO2 refrigerant for hot water. And that's because it's a high pressure product and doesn't really work that well when it's being asked to do a lot of space heating. The combination space heating products and domestic hot water use either R32 or they use R410A, and they're not very popular. It's simply much more effective and easier to use two different products to do the same thing, as we talked about. But CO2 makes a great amount of hot water. It's a simply great refrigerant for hot water. But it's a unitary product, meaning the outdoor unit, as you see on the left-hand picture, it makes hot water in and of itself. They use a storage tank to allow the compressor to run at a low volume for a long period of time and take a great quantity of water and store the energy in it. As you see on the right, that's like what they call a monoblock style. It's literally got a small vessel of water in it, but the water then is piped from outside to inside. And that's a common form factor that we see all over Asia. And there's some in the US too, actually. So let's move to the next slide. The out there, not really common in the US, but they are in China in particular, and some in Japan, are split systems where there's an outdoor unit that looks just like a ductless heat pump, and there's refrigerant lines that connect it to an indoor tank. And easy to install, pretty cost optimized, and really made by all the major brands in China in particular that I've seen. And the picture that you see there, it has a great user interface that works pretty much like the unitary, like GE GeoSpring or AO Smith or Rheem. It has a nice interface on the tank. And then you just connect water to the tank and power to the tank. And then you run refrigerant lines to the outdoor unit and a power and communications wire to the outdoor unit. And it's a very simple installation. And it's very much more a residential split system type product with capacities in water tank around 30 to 50 or 80 gallons. Currently, everything I'm seeing uses R410A, which has its advantages for something that's a split system. It's just simply accepted and known from an installation contractor standpoint. Okay, let's go to the next slide. And this is a product, Sean, that is, I think, something that will be interesting to you, especially at scale. And so there's, again, several manufacturers out there that make this product. It's literally common out there. And it would sit on a commercial building rooftop or a mechanical area outside, and you would pipe water into the structure. You see the 3 stainless steel pipes coming out of this. This unit can be used for either space heating and or conditioning. But again, I don't think you see the efficiencies when you do that. But nevertheless, it's a product that's designed a little bit for that. The cool thing is about these kinds of products is if you have a need for some pretty large capacities, multifamily and so forth, you can basically commonly manifold pipe the water and use a communications wire between multiples of this unit. And much like in a VRF system in commercial buildings, the compressors work together to produce the demand. So it's a pretty smart, intelligent system. It can be used for just domestic hot water. Because it's using 410A, you can get multiple storage tanks and put a cold water storage tank in the structure and do air conditioning and heating. But you dramatically, very quickly use more power because the compressor is going to be running just a lot. It'll switch from making domestic hot water, it'll stop, change some valves, and then run to make chilled water for air conditioning. And it'll do that all day until until somebody runs hot water, and then it'll stop, refresh the hot water. And so you just have a really big compressor that'll run all the time if you use it as a combination space heating system. That being said, it can do it. So let's move to the next slide. And I would love to take some questions. I saw some good ones flash up on my screen. Obviously, you can tell I'm not a huge fan about the combination domestic hot water and air conditioning, but it's very easy for me to say don't do it when I'm not being asked to design buildings with no space like I'm gathering that Sean has. So that's all I know for now, and I'm going to...
Why don't you answer these questions here? If you saw some questions, go ahead and jump on them.
Okay, so I'll just start and work backwards. So how optimistic am I about effective leak control and capturing of refrigerants? Very confident about it. But that being said, it all depends on the tradesperson involved. I mean, I would love to say that plumbers never have leaks of newly installed systems, right? But they do. And the same with refrigerant. That being said, copper tubes are pretty, and flare fittings, which is what these use, are very effective when done right. So it's really, it's not something I think we can absolutely regulate out or technologically eliminate. But if we do a good job with training, you know, we don't see a lot of fires with electrical because tradespeople are really well trained. So I'm hopeful.
Another question I got, an interesting one here. So Robert asked me privately, why was I not a fan of the combination systems? And to reinforce what you're saying, there's a trade-off. The combination systems, they take more solar to power because they're less efficient. They also take more money to buy because the controls are expensive. To switch it back and forth or to have a combination box with valves and controls, they're actually an expensive piece of equipment in addition to just the normal jobs they do. So what they're supposed to do is save construction costs on space, because you don't have to put as many products in or have it all just controlled in one place. Like there's some other arguments that people have, but they are more expensive and they take more energy. And they
because
save somewhere else.
Being asked to do so much too, Sean, keep in mind that they, you know, to do both spacing, and both is they're a bigger compressor, right? Because the compressor has to be sized for the BTUs as well as, you know, the type of refrigerant application. So they just run a lot. And that's, I mean, if you don't care about energy and you can afford to, yeah, why not? Right. But I think for our audience, we're trying to balance multiple objectives, and I think it's just hard.
The balance is solar powering it on site, because this is a Z&E conference. And what I've seen is that the central systems are not impossible to balance on site, you know, the increased energy consumption, but it is a new extra load. So
there's the complicated controls that you talked about. So from an implementation standpoint, I think those are going to be really, this was at the big heating and air conditioning expo, and there's some really neat manifold controls. There's some really neat, just intelligent equipment coming out that, I mean, if you could offset the load with solar, it may not be a really bad choice for you. as long as you can put enough solar to offset it.
You want to
And,
answer
you know, in a space compromised place, right?
why don't you answer one more question here? If you saw one you wanted to answer, it looks like some more questions about leaks, but go ahead.
Yeah, let's look at
Propane.
them real quick and see. Okay, I had previously seen propane listed as a potential refrigerant. Yes, the GWP is great, but flammability sounds like a recipe, right? Okay, yeah, I mean, all of the same conversations that we had in the previous presentation about you know, natural gas being piped around and the potential for leaks is the same with propane. And propane has great refrigerant properties. So does ammonia gas, believe it or not, ammonia gas. So we would have to just make a unitary product, meaning that we would never have a installer trying to put refrigerant lines in place and making the connections. It would simply be just something that stands alone, just like you get with the sand end product, which is operates at such high pressures. It has to be a unitary product. And so propane and ammonia are great because they're that mid-temp refrigerant that can do both heating and cooling, whereas CO2 is really just a heating product.
Right. So with that, we're going to transfer this over to Christine Tam. Thank you, Jonathan. Yay! Good job.
Thanks, John. Talk to you soon, everybody. Thank you.
Talk to you soon. So Christine, she works for the city of Palo Alto in their utilities department, and she is a leader there in the decarbonization effort. And this is our last presentation, Christine, and then we'll take an hour-and-a-half break. We'll return at 1:30 of California time. So Christine, please take it away.